investigate.
It wasn't this computer.
It does feel suspiciously hot, like it's still thinking, oh, you stupid computer, I told you to sleep. Idiot.
Oh, I just noticed you changed up the other stickers in your computer.
Yes, I have a variety. I have got, as you can see.
I mean, I'm not upset with the cruise sticker.
Yeah, of course I have the crew sticker. This was another Dragon Ball Z sticker, but Matthew has this need to peel off stickers. I need to replace that. And then, of course, you have your random collection of Dragon Ball Zs. You got some Dragon Balls. You got your Goku, Prince of Saiyans, Mr. Piccolo, your Frieza. You know, the good stuff. Let's see here. Oh, where was I? Trying to make this thing sleep, right? Sleep. That's sleep. Good. Very good. Now, back in chapter 1, all right, and it's really important that you guys read chapter 1 to really appreciate this book for what it is. Chapter 1 is a really nice book, nice chapter. Very big picture. Would be horrible to lecture from, I think. But one of the things, until I know a lot more, back his definition 1.4 is as follows. All right. Here's his definition 1.4. Let me write it down for you. So here was definition 1.4. He said for X, a subset of Rn, and for Y, a subset of Rm, all right, a map F from X to Y is called continuous right? It's called continuous if for any subset A of X and any X in X adherent to A, right? The point f of x adheres to f of a. So in chapter 1, this is totally geometric. All right? Like he really has this idea of gluing. So, you know, like basically here's a picture, here's a point x, it's glued to, you know, it's glued to x, let's say, right? And then over here, you know, I guess it's fine. It's maybe x is bigger. This is a, so x could be like this, right? And then over here, we've got some other space, right? Y, and f of a could be something like this, right? So if x is adhere, what he's saying is it can't be that you got like f of x out here. It has to be, it has to adhere to f of a. It has to be in here somewhere, right? If f is continuous, it can't just jump off the image, right? Unless, of course, the point is isolated in the domain as well. Right? If the point in the domain doesn't adhere to the other points in the domain, in the sense of being adherent to some common subset, right? We talk about isolated points in advanced calculus sometimes, not always, but so like, in fact, I'll make a separate definition for a limit of a function at an isolated point. We have limit points, we have isolated points, and I don't think I got into it last time because I didn't think it was that interesting, but anyway, so that's essentially geometric idea. Now, this on the other hand, we've built up this notion of closure, right? And continuity, just in terms of set theory. And it's the same, right? What is this? This lemma says that if,
X adheres to A.
yeah, exactly, he says if X adheres to A, then X adheres, then the image, well, you know, so basically if X is an element of A closure, which means X adheres to A, that implies that f of X, what?
Summit of F of A.
F of A closure. Right? I mean, I'm getting to the punchline. I wasn't trying to prove it. And there you go. That is in concert with his original geometric definition of continuity, which is that a continuous map doesn't rip points that are stuck to other points away from them under the mapping. I think that's a wonderful thing to say, because you talk about inverse images of open sets and all these other things, and you just could lose track of what's the basic idea of continuity. And I also like that this notion of adherence of a point, it's not just about sets, it's also this notion of continuity for a set. This notion that a point is adherent to the set if it's in the closure. Right? So we're putting this notion of adherence of the sticking of points to sets and this notion of points sticking to images on the same footing. We're combining these concepts of continuity and, you know, a certain type of geometric attachment of points to a set. That's definitely been lost in certain families of definitions I've worked with in courses. I mean, I always, of course, we all have an intuitive sense of what a continuous function is, but a lot of that's more built around our knowledge of continuous functions. Like, it's a polynomial, it's a sine, it's a cosine, it's a, you know, it's all these fun things where the graph isn't weird. But this I like this a lot. How do we prove this? So I guess we should prove this if it's important, right? Yeah, looks like we're still in chapter 3 next week. I'm sorry, guys. You can forgive me, I hope. I think we'll be past chapter 3 next week. I think I need one more meeting for, like, the next meeting. Hopefully we'll talk about subspaces and immersions, as well as the product topology business. But I think it's important to go slow through these things. They really help you understand what a topology is and how the definitions work. There's no sense in hurrying them. That's the whole point of what we're doing. Okay. There's also some things in the metric space section which I have not talked about. I probably won't talk about them in here. Just want you guys to read it. But there's a little bit more than what we did in there, you'll see. Especially his notion of equivalent. And it's this discussion of when spaces are metrizable or not. There's a little bit more there. Maybe we'll come back to that some other day. Let's see here. Let me get back. Focus. All right. So what do we got here? Let me follow his proof. If you guys are as tired as I am, probably be helpful. If f is continuous, then what do we know? If A is a subset of X, right, then this is a bit of a jump. The inverse image of the closure of f of A is closed.
What?
And contains A.
Okay, well, the closure of f of A is closed, and we know that the pre-image of a closed set is also closed since f is continuous.
Ah, very good. Right. That we proved last time. The inverse image of a closed set is closed under a continuous map. That's a closed set. Inverse image of closed set is closed. Very good. Now why does it contain A?
Because the closure of f of A contains f of A. So f inverse of that contains A.
So what you're saying is that f inverse, I think I know what you're saying. You're saying f of A is a subset of the closure of f of A. And so the F inverse of f of a is contained in F inverse of the closure of f of a. But A is contained in there, right? Hence, this contains A.
So that wasn't too bad.
Therefore what? It is bad if we forget what we did before.
Yeah.
If we forget what we did before, then we'd have to redo all that again in the context of this proof, in this particular situation. Much like the Calculus 2 student who forgets that the integral of secant squared is basic. We would pay a price for our ignorance. Thankfully, you guys have a memory that's better than mine, so we'll move on. So it's closed and contains A. What's that mean?
It means it's a subset of the closure of A.
Right. So therefore, we have that a closure, right, is a subset of the inverse image of the closure of f of A. Right? Because the closure of A is the intersection of all closed sets containing A. So, right. Yeah. So then what? What's that say then? From this we can see that f of a closure is a subset of f of a closure. Sorry. The closure of f of A. Which is good, because that's what we're trying to prove. Right? Again, that says that that's that adherence condition written in terms of closures and such. So we've just proved this from assuming continuity.
It's 5:00 p.m.
Silence, woman! Sorry, I should be more open-minded. I'm kind of Neanderthal, am I? Talking to electronic women this way. My goodness. Or someone watches this and gets the wrong idea.
You should get one that like has Trump's voice. It's 5:00. We're gonna win this thing.
I was hoping you'd say something that would be like huge or big. Those are my favorite.
It's 2 Corinthians o'clock.
President Trump. All right. Other direction. We do what? We assume that f of the image of the closure is a subset of the closure of the image. What do we want to do? Wish to prove f is continuous, right? How do we do that? I guess we got a lot of options because we have a few equivalent statements for continuity of f, right? Let's see which one. I wonder if he was going to go straight from the definition or do something sneakier. Seems likely he's going to do something with closed sets, doesn't it?
Yeah.
He can show the inverse image of closed sets as once more closed. I guess he'll be good to go, right? Okay, so yeah, that's what he does. So let's look at C, a subset of Y, a closed set. So what's that mean?
minus C. No, wait, no.
Yeah, it means y minus c is open. But then he says let, basically, or set A equal to the inverse image of that closed set C. All right? And now let's use what we're given. So f of the closure of f inverse of C, again, so we're letting that play the role of A, is a subset of what? That's a subset of f inverse of C closure by the assumption, right? Now, so he says that this is just equal to C. Can you see why that's true? Oh, I'm sorry.
Right, because f of f inverse of C is C, and the closure of a closed set is just C.
So
Hmm. Right. Then he writes, he actually writes, yeah, I missed a step. He says that this is clearly C, and then that's equal to, yeah, just like you said, C. So what's that mean? Ooh, you don't see that too much. Whence?
Except with Scamortis.
Thence? F inverse of C. Although this is a translation of an Italian, so there's no telling what it really says. Like say something racist about pizza at the moment, but I'm not going to. Let's see here. C. All right. F inverse. I used to know Italian in grad school. Riccardo Ricci. That guy was awesome. I mean, he was really good. Let's see here. I wonder what he's doing. F inverse of C. How is that clear? Oh, he just takes the inverse image of this up here, right? So the inverse image of this is a subset of the inverse image of that,
Right.
because inverse images preserve subsets. And the inverse image of F is the thing inside again, right? So the inverse image of this is just that. Right. What was that saying?
Well, f inverse of C is a subset of its closure, so that means they have to be equal.
Right, but like you just said, F inverse of C is also a subset of its closure, so that means we get what? We have dual containment. Was it as it is known in the other classes you take, uber containment? No? Anyway. I actually kind of like that statement, it's funny. Although it seems that the word uber is going to soon have a different meaning, which is disconnected from its previous more nerdy meetings. Yeah. Which is to say that the inverse image is closed. And there you have it. The inverse image of a closed set is closed. A closed set was arbitrary. Therefore, F is continuous. All right. Do I have like 5 more minutes?
Yeah.
Okay. There's some things I need to finish today because we have on our mind all these things and we use them. So, you okay, John?
Oh, yeah, I'm good. Just copying down the last bit there.
Definition, as I had advertised at the start, we'll eventually get the definition for continuity at a point. We're almost there. So, definition, a map F between topological spaces is continuous at a point I'm sorry. I got fished in at a point x in X. If for any neighborhood U of f of x, there exists a neighborhood V of x such that what? F of V is a subset of U. So this has contained within it this idea that you can find open sets around the image point and open sets around the, inverse image of that is, again, it has this idea of inverse images of open sets around the points, kind of tied up in this notion of local neighborhood, right? And here's the theorem. It might be interesting to think about this definition as it applies to weirder things, like a sequence or something, I don't know. Okay, so a map F from X to Y is continuous if and only if what?
It's continuous for all x on the x.
Indeed. At each x in X. Now the next page is the stuff we proved last time about homeomorphisms. Now the proof of this, I'll just read it for you. Suppose f is continuous, and let u be a neighborhood of f of x. By definition of neighborhood, there's an open set A of y such that f of x is an element of A is a subset of u. The open set V equals f inverse of A is a neighborhood of x, and f of V is fine. I can't. Reading it doesn't mean anything. I can't do anything without a picture. So here's x. Here's y. He says f continuous, neighborhood of f of x. So here's f of x. Here's x. Open set A of y. Such that f of x is an element of A is a subset of u. Where's u? Oh, u is the neighborhood. So u is, sorry, I should have drawn u first. U is something bigger, right? And then what do you say?
That's just by the definition of a neighborhood.
Right, exactly. He says the open set V equals f inverse of A, so just and now I know that's open because it's the inverse image of an open set. Right? Assuming f is continuous. That is what? That's a neighborhood. This is a neighborhood of X.
Boringly, I guess.
Right? And what else? F of V is what? It's a subset of U, right? Because the image of V
It's just going to be A.
is A, which is subset of U. And that's the forward implication. And I'll let you guys read the reverse implication because I've kept you guys long enough today. But it's on page 47. And it is similar. And there you have it. Continuity and everything, not a limit to be seen. There is a notion of limit that we'll talk about hopefully later. And it's interesting, the general concept of limit, it's not unique. Like you can have limits in topological spaces where it's not just one thing. Like this limit being unique as we're used to it only happens in certain nice spaces. In less nice spaces, limits aren't unique, and they're not. But then there's suitable complications, or there's ways of bumping it up so it works again. Anyway, I'll stop. Thanks, guys.